Okay, join me in your science book on page 246. If you go ahead and look at the picture on your screen first, you can see these convection currents. Okay, so you see this is the cold water from the north up by Alaska. Cold water comes down along the California coast. This line is the equator. It gets heated up, starts heading north again, and then as it heads north, it cools. And we have this convection current going on. Okay, now you have the opposite, everything going in the opposite direction in the southern hemisphere because we're south of the equator. So here you have the cold water near the South Pole, and that cold water starts moving in towards the equator, gets warmed up by the direct sunlight that hits the equator, heats that up, and it starts to move out. And then it starts to cool again because now they're getting close to the South Pole where it's much colder because a lot less direct sunlight and so on. Okay. All right, join me on page 246 and you can see an example of the major ocean currents on the top of page 246 as well. Looks a little different than mine, but fairly similar. A lot of similarities actually. What causes ocean currents? An ocean current is a continuous flow of water along a definite path. To visualize an ocean current, try to imagine a river, such as the Mississippi River, flowing through the sea. Like wind currents, ocean currents form because of the uneven heating of Earth's surface by the sun. Ocean currents carry warm water away from areas near the equator to the polar regions. These convection currents also move cold water from the polar regions to the lower latitudes, or closer to the equator is what that means. Winds propel some ocean currents on the surface. Other currents move deep beneath the surface. Factors such as temperature and density influence the movement of ocean currents. Salinity, the amount of salt in water, changes the density of the water. Salinity can also affect the currents. Surface currents. Winds blowing steadily across the ocean can cause the top layer of the water to move in huge circular patterns. Surface currents can move at speeds of about 120 kilometers or 75 miles per day. These currents may move water hundreds of kilometers through the ocean. As currents flow along the edges of continents, the currents affect the land's climate. One of the strongest ocean currents in the world is the Gulf Stream, which carries warm water from the southern tip of Florida north along the eastern coast of the United States. The Gulf Stream not only keeps the east coast of the United States warm, but also keeps parts of northern Europe from freezing. By contrast, the California current carries cold water toward the equator along the west coast of the United States, keeping the climate of the Northwest cool. The Coriolis effect causes currents to bend to the right or clockwise in the northern hemisphere and to the left or counterclockwise in the southern hemisphere. The currents then start flowing in huge circles, forming a continuous global pattern of water circulation. The presence of coasts or land masses also affects the flow of the surface currents. Deep water currents. Colder, saltier water is denser than warmer, less salty water. Cold, dense water flowing from polar regions moves under warmer, less dense water. As the colder currents move toward the equator, they become warmer and rise to the surface. Warm waters from these regions flow toward the poles, where they cool down and begin to sink. The water in a deep water current moves much more slowly than the water in a surface current, just a few meters per day. However, deep water currents take up a much larger part of the ocean than surface currents do. Sea breezes. Another example of convection at work is a breeze that occurs along a coastline. Because land heats up faster than water, the air above land is warmer during the day than the air over a nearby body of water. The warm air expands and rises. The cooler air above the water moves in and replaces the rising warm air. A sea breeze is a wind that blows from the sea toward the land. At night, the process reverses. The air over the land cools more rapidly than the air over the water. Winds blow from the land to the sea, producing a land breeze. Okay, turning the page. Page 248. What is El Nino/Southern Oscillation? Convection currents in oceans have a tremendous influence on world climates. Winds move currents as they blow across the oceans. Ocean currents, in turn, interact with the atmosphere. Any disruption in these systems can cause climate changes. Under normal conditions, the trade winds near the equator blow toward the west. Warm surface water builds up in the western Pacific Ocean along the western coast of South America. Water from deeper levels of the ocean moves up to the surface. The cold, nutrient-rich water supports large numbers of fish. Every few years, the surface waters near Peru and Ecuador become unusually warm. As a result, the water holds fewer nutrients, so there are fewer fish, and fish-eating birds die. People working in the area have been aware of this pattern, called El Nino, for centuries. During most years, strong winds from the North American and South American coastlines push warm water across the Pacific toward Australia and Japan. When the warm water moves to the west, cold water rises to the surface to replace it. During El Nino years, which occur every 3 to 7 years, the wind is weak and little water is pushed across the Pacific. With no cold water rising, the ocean stays warm. Scientists use the term ENSO, or El Nino Southern Oscillation, to refer to the disruption of the ocean atmosphere system in the Pacific Ocean and the impact that it has on weather around the globe. The word oscillate means to swing back and forth. The Southern Oscillation is a back and forth pattern of reversing surface air pressure between the eastern and western Pacific Ocean along the equator. ENSO may come and go quickly, or it may last for several months. When the equatorial Pacific waters become unusually cold, a La Nina may form. Effects of ENSO. Scientists are not sure of the cause and effect relationship between the changes in the atmosphere and the changes in the ocean during El Nino. They do not know whether pressure reversals in the atmosphere cause NESO or NESO causes the changes in the atmosphere. So now I'm on the top of page 249. They do know that there are very dramatic climate changes during ENSO. In the ocean, the cold water carries nutrients for marine life. Without the new nutrients, large numbers of fish and other organisms die. During ENSO, the entire food chain is affected. On land, weather patterns across the world change. Areas that are usually dry may receive a great deal of rain, and areas that are usually wet may experience droughts. ENSO often brings heavy storms to the Gulf of Mexico, Peru, Ecuador, Bolivia, and Cuba, causing landslides and floods. Other areas, such as Southern Africa, Central and South America, Indonesia, and the Philippines, and India, are hit with extreme drought. This can lead to famine and loss of life. During the last ENSO, California experienced serious storms that led to floods and mudslides. In addition to its impact on regions in the Pacific, ENSO causes changes in the path of the jet stream, a current of fast-moving air in the upper atmosphere. The jet stream is one factor that determines weather in North America. Okay, turning the page to page 250. Follow along. How do convection currents work underground? Earth consists of 3 main sections: the crust, the mantle, the core. and the core, excuse me. The temperature of the inner core reaches 5,500 degrees Fahrenheit, or 9,932 degrees Fahrenheit, 5,500 degrees Celsius, excuse me. Temperatures in the mantle are much cooler, but still quite hot. The mantle consists of soft, yielding rock material that slowly moves in currents like other fluids. This material is cooler and denser closer to the crust. Because rock is a poor conductor of heat, most of the transfer of heat in Earth's interior occurs through convection currents. The rock material in Earth's mantle rises and falls. The cooler material sinks toward the core. Warmer, less dense material rises. This cycle distributes heat from Earth's core throughout the mantle. And you could see that in the picture at the bottom on page 250. We see again that continuous circling of hot and cold. Only a small amount of heat from Earth's interior reaches the atmosphere. The rocks in the Earth's interior insulate the surface from the core's heat better than the clouds and atmosphere insulate the surface from the sun. Heat from the core takes longer to reach Earth's surface than the sun's heat takes to reach Earth. Because of this, most of the heat on Earth's surface is from the sun, not from Earth's core. Power for plate tectonics. Convection currents in the mantle push rock against the bottom of Earth's crust. This movement causes Earth's plates to move along Earth's surface, causing earthquakes and slow motions of the crust. Sometimes convection rises as a column or plume of molten rock, producing a hot spot. These hot spots erupt as volcanoes. Examples of a convection hot spots are the Hawaiian Islands and the volcanic features of Yellowstone National Park, such as geysers and hot springs. All right, thanks for watching and following along. You can continue in your science lesson in your Google Classroom, and I'll see you on the next one.